Hi guys, welcome to part 2 of the Segmentary series. So in this part, we will be mainly focusing on the implementation of a segmentary, and we will also be seeing some variants of the segmentary. So let's directly get started. So before starting with the implementation, let us first discuss that how the implementation will be. So so let me just draw a simple segmentary that we will have. So yeah, so I have just drawn four nodes this time for the segmentary. So let us quickly discuss how we will implement. First, here I will write how we will implement the update functionality, and here I will write how I will implement the range sum functionality. Now it's easy over here. So we already discussed for updates. Say we want to update this node, then we have to update all its ancestors. So say this was 5 earlier, and then now it got updated to 8, then this also will increase by 3, and this also will increase by 3. So now if you have studied binary heaps, you would know that if a node is x, then its children will be 2x plus 1 and 2x plus 2. So I will just show uh, short like in short how it works. So let's say this is node 0. So this is not the sum, so this is the just the number of the node. Okay, so this is node 0. So if we take 2x plus 1, then this is 1, and 2x plus 2, it is 2. Now if we take 2x plus 1 where x is 1, then its child will be 3 and 4. And similarly for this 2x plus 1, so 2x plus 1 where it is x, therefore this will be 5, and right child will be 6. So this is how it works. So what we are going to do is we are going to take the current node as x and its left child, so left child as 2x plus 1 and right child as 2x plus 2. Now so this is about the child. Now for the update, so it is quite easy. What we'll do, say we have so we are getting the input of the ith element, so the ith index that we have to update with value. So what we will do is we will just check if I, so now it is pretty clear that each node will have a segment associated with it, and a segment will be like Lx will be the left bound of the segment and Rx will be the right bound of the segment. So each node will have a segment associated with it. So now what we will do, we will define a mid, and we will just check that the element that we have to update, does it lie in the left segment or does it lie in the right segment. And if we start from the root node, let us say we have to update this element. So this root node, so it is the whole segment, so its segment has all of these elements, right, all of these four elements. So here I will lie in the left segment. Now therefore we will go to the left child. Here I lies in the right segment, so then we will go to the right child, all the while updating, right. And once we reach the right child, we will just like update the value over here. So that we will see how to do in the implementation. And the range something we already discussed, but let me discuss it once again, that how the range sum will work. So the range sum will work something similarly, that for each node we have the segment associated with that node, with Lx being the left bound of that segment and Rx being the right bound. So we will again define a mid, and we will again check for its left subtree and its right subtree, right. So each node will have two children. So again 2x plus 1 is its left child node, and 2x plus 2 is its right child node. So this was just a brief on how we will implement. Now let us directly jump to the C++ code. Now basically what I'm going to be doing in the C++ code, that I'm going to be implementing the class segmentary, so that we can directly create objects and create as many segmentaries of that type as we want. So yeah, let us directly now go to the implementation. Okay, so now let us start with the implementation. But before we start with the implementation, I would like to thank Pashka for this super clean implementation. So yeah, now let's begin. So first thing that we'll do is that we will define the class Segtree. So now in the Segtree class, first thing that we are going to be doing is that we are going to we are going to initialize the segment tree. So for initialize the segment tree, first we need to define two things. That first we need to define the size of the segment tree. Now as we discussed, we know that the size of the segment tree needs to be always a power of 2, so that we will be able to make a complete binary tree. So this, let me define a vector with vector int tree. Now let us start. So first I will initialize with size equal to 1. Now while size is less than n, I will keep multiplying size by 2. So that means we will reach the nearest power of 2 which is greater than n. So this is simply what it does. And now as we know that we have to assign 2 times that much space, because as we know, a complete binary tree of n nodes requires 2n space, right? So we are going to assign 2 into size initialized with 0. So this is the init function. Now the first function that we will be writing is the update function. So the update function is again a void function. So let us see what we have. So the arguments for the update function, it will be int I and int value. So basically it is the value which has to be updated at which index. So now here I'm going to do that. I'm going to call a same overloaded function but with different parameters. So the parameters for that function, it will be again I value 0, which is the node 0, and the left and right bound of the segment. So the left bound of the root node is obviously 0, and the right bound of the root node, that is the right bound of the segment, is the size of the tree. So I will now write the overloaded function over here, which is int I, int val, int x, which is the node, and its bounds. So int lx and int rx. Now in update, what we will do? So here what we are going to do is, first thing in the update, we will see if I is less than mid, go to left. If I is greater than equal to mid, then we'll go to the right child. But before all this, we will see if segment size is 1, then we will update the value. So what do we exactly mean by segment size 1? So lx minus, if rx minus lx is equal to 1, therefore we have already reached the leaf node, that is we have to directly update the value. So let us implement this first, that if rx minus lx is equal to 1, then simply tree of x is equal to value, and we have to directly return from here. So this is done. Next what we will do is we will define int mid is equal to lx plus rx divided by 2. So now here we are directly going to check if I is less than mid, then we will go to the, simply go to the left child, right? So the left child is, we will call the recursive function. So it is nothing but I comma val comma, now the left child, as we discussed, it is always 2 into x plus 1. And now the bounds of the left child, it will be lx comma mid, right? And it's obvious that the bounds of the right child will be it will be mid comma rx. So else we will update I comma val comma 2x plus 2 comma mid comma rx. Now reaching here, the last thing that we have to do is that we have to update the value of the xth node. What will be the value of the xth node? Obviously it will be the sum of its children. So it will be tree of x is equal to tree of 2x plus 1, tree of 2x plus 2. So yeah, I think we are done with our update function here. So let us see for once if everything is satisfied. Yeah, go to left, go to right, and if segment size is 1, then we have updated the value. Now let us go and let us try and write the sum function. So now the sum function will have a return type of int. So int l comma int r. Now again we will write the overloaded sum function. to get a recursive call. So we will return sum int l comma int sum l comma r, and again the parameters will be, we'll start from the 0th node whose the segment bounds are 0 comma size. Now again we will write the overloaded sum function, which will have the parameters int l, int r, int x, int lx comma int rx. And now, so let us check the three cases that we have for our range sum function. So the first case is that the l comma r range, so our segment lies entirely outside the l comma r range. So now let us just write the code for it. So we can easily see that if l is greater than rx, so if l is greater than equal to rx, or it will be the same thing that if if lx is, so let us imagine that this is over here. So let me write it. If it is something like this, where this is l comma r, so this is where lx is greater than or equal to r, right? So if lx is greater than or equal to r, then we have nothing to return, because both our segment do not intersect at all. So this is our first case. So let us move to the second case, where we have our entire segment lying inside the given range. So in this case, what we will do is we will write if lx is greater than equal to l and rx is less than equal to r. So if lx is greater than or equal to l and rx is less than or equal to r, then what we will do, we will simply return the value of that node. And what is the value of that node? It is tree of x. Now the third case is that it is partially intersecting. So now in this case, what we do, it's pretty easy. What we do, we just go to their child nodes. So here again we will calculate in mid is equal to lx plus rx divided by 2. Now we will calculate the sum of each of the child nodes. So it is nothing but sum of, so the range will remain the same, but the node will change. Now it will become 2 into x plus 1 comma the its bounds will be lx comma mid, since it is the left child, and int s2, which is the right child, it will be sum l comma r comma 2 into x plus 2, and its bounds will again be mid comma rx. Now we have got the answer for its children. What we have to do is, for this couple of arguments, we have to do nothing but return the sum of s1 comma s2, right? And it will continue to go in the recursion. So we have done this. So I think we have completed our sum and update function. So how to exactly use these functions in a segment tree? So here we have int n as our input. So n is the number of size of our array. So the first thing that we'll do is, so now here you see we have already initialized the object st of the segment tree. So here first thing that we are going to do is that we are going to initialize the segment tree. So our initialize function, as you saw, it is nothing but it takes the nearest power of 2, which is greater than n. Now coming to st dot init n. So now let us take input a simple array, so vector a of n, and let us take, say, for int I is equal to 0, and let us take input the array. So now when we are taking input the array, so okay, let's just take a scene a of I, and when we are taking input the array, let us just construct the segment tree then and there. So here, how do we construct the segment tree? We will update the ith element of the segment tree with ai. So simply update I comma ai. And since these functions are overloaded, it will choose this function because it has 2 arguments. So now update I comma ai is done. So now let us say we have q queries, scene q. So while q minus minus, so we have 2 types of queries, as we already discussed. So the first type of query is 1 I comma v, which is the update query, right? And the second type of query is 2 l comma r, which is the sum between l and r minus 1. So yeah, we can use this. So let's just take a small example over here. So let us take int type. So C in type. So if type equal to 1, so if type equal to 1, then we will take input I comma v, two integers. Yeah, and we have to just call the update function. So update, sorry, all of this will be st dot update. Sorry for the error. So I comma v. Yeah, and the else it will be, yeah. So for else it will be int l comma r and scene l comma r, and here we are going to just output st dot sum l comma r. So yeah, this is the working code, and let us now just test a small example on this. So let me compile it. So taking a small example, let us now take first, we have n. So let us take, say, n is equal to 5, and now let us enter the elements of the array. So 2, 3, 4, 1, 5 are the elements of the array. Now let us take first, let us take two queries on the array. So two queries, and let us first have a type 1 query. Let us update this 3 to a 6. So 1 1 6. So it is done, and now let us have a type 2 query where we will check the sum of the first two elements. So now since we know the second element is 6, the sum of the first two elements should be 8. So 2 0 2. So yes, we got our answer. The sum of the first two elements is 8. So this was all about the implementation. Now next we are going to quickly discuss all the variants of this type of segmentary, and as you will notice, the code does not change much. It is just minor change here and there. So now the next variant that we are going to discuss is the minimum segmentary. That is our range function will give us the minimum between L comma R. So let us proceed. Okay, so let us see another type of segmentary. So in this segmentary, we will again have the two operations, which is update any index I with the value, and the second type of operation that we will have, that find the minimum in range of index L comma R. So this will be the operations. So now if you see, I will show you how we will construct the segmentary, and you will see there is not much difference from the segmentary that we had constructed earlier for the sum. So let us construct the segmentary now. So here let us take the leaf nodes. So we already know now that the leaf nodes are the elements of the array. So let us take 1 2 5 3 2 1, say 0, and let us take so let us make it a perfect 8. So let us take 7. Now to construct the min segmentary, first what we will do is, now instead of taking the sum of these two elements to be their parent node, what we will do is we will just take the min of these two elements. So the min of 7 comma 1 is just 1, and the min of 2 comma 5 is 2. So the min of 3 comma 2 is 2, and the min of 1 and 0 is 0. And again going up, so the parent of these two, the min of 1 comma 2 is 1, and the min of 2 and 0 is 0. And finally the root node, it will be the min of 1 and 0, which is 0. Now if you see, we can exactly keep the operations same, and instead of where we are doing sum in the initial segmentary, we can just replace it with minimum. So now let us directly go to the code, and I will just show you where to change to convert the sum segmentary into the minimum segmentary. So let's see. Now let us see the code for the minimum segmentary. So here let us see the changes that we have to make. So there are not many changes. So the first basic change that we are going to do is that instead of initializing the tree with 0, we can initialize the tree with some big number, so that the extra nodes do not cause any like disturbance in the original, like the minimum so the minimum of a node of the tree and an extra node that you added just to make it a complete binary tree. So the minimum of them will always be an element of the array. So yeah. Now going to the update function or the set function, as I've written here. Here instead of taking sum, we have just taken minimum of the two child nodes, right? So, and one more change will be that here instead of returning 0, we will return maximum. Because why we will return maximum? Because the minimum of any pair with maximum will always return the other number. So that's why we will return maximum over here. Also here instead of returning s1 plus s2 as we did over here, here you can see we returned s1 plus s2. So here obviously we will return minimum of s1 comma s2. So this is about all the difference that the two segment trees will have, and this segment tree will produce a minimum value. So this will be a minimum segment tree, so range minimum segment tree. So yeah, so you can try to implement this by yourself. And so this is basically the end of the segmentary session. So next we will be discussing Fenwick trees. And now, so basically these two videos were on segment trees, and you can try by yourself various segment trees like maximum, so range maximum segment trees, range GCD segment trees, range XOR segment trees, and you will see that there is not much difference in implementation. Okay. So yeah, so let me know if you have any doubts, and thank you.